SwayamPrabha. Digital India. Educated India.
Hello. So, welcome to lecture 17. We will continue bidirectional bending of beam in this lecture 2. So, let us so in the last class we have derived the expression of the normal stress in a beam which is experiencing bidirectional moment mx and my, and we have found out the expression of the normal stress sigma z. So, we have found out normal stress sigma z in terms of the applied moment mx, my and the sectional property and x and y. So, what we have done, if we have a beam with any boundary condition, here I have drawn a cantilever beam with a length L and the coordinate axes are shown with a green color. Z axis is the lengthwise axis of the beam, x and y are the cross sectional axis of the beam. The two bending moments my and mx are added about the x and y axis. They are positive if they produce tension in the first quadrant of the cross section. So, we have taken any arbitrary section AA of the beam and on the right hand side we have drawn the section AA. Now, in AA section, if I the axis of the cross section is x and y as I said earlier, and the moment that are acting is my and mx. So, these are the moments that are acting on the so these are the moment that is acting on. So, both mx and my are positive according to our sign convention. So, then we have said that if we take any arbitrary point P on the cross section, then sigma z P at that point or the normal stress at that point P can be written in this form, where x p is the coordinate of x coordinate of point P and y p is the y coordinate of the point P. And therefore, by this equation which I called as equation 1, we can obtain the expression of sigma z at any arbitrary point on the cross section. Now, if we further rearrange this expression, then sigma z can actually be written as my or mx Iyy into y minus So, I can rearrange equation 1 in this form of equation 2, where I separate out the coefficient of the moment mx and my separately. Okay. Now, let us so now let us find out this angle alpha. Alpha is the angle that the neutral axis makes. The neutral axis makes with the horizontal x axis. Now, how do I find out this angle alpha? Now, as we all know that neutral axis is the line and about at which the stresses are equal to 0. So, we will use this definition of neutral axis to find out the expression for alpha. So, what we will be doing is we will be equating from equation 1 equating sigma z equals to 0 for obtaining for the neutral axis. We can say that it is going to be, so 0 is going to be my ixx minus mx ixy by ixx iyy minus ixy square into x of neutral axis. So, if I choose any arbitrary point on the neutral axis, then the x of the neutral axis and y of the neutral axis. So, this is x n a and this is y n a. So, x of neutral axis plus mx iyy minus my ixx xy into y of neutral axis. Now, this has to be equated to 0. Then also we can say that tan alpha can be written as y of neutral axis by x of neutral axis. So, from the above equation, if we find out the ratio of y of neutral axis by x of neutral axis, we will get my into ixx minus mx divided by my ixy minus mx iyy. So, this is what we are going to get the expression for tan alpha. So, therefore, by solving this equation 3, we can get the expression to obtain the angle alpha that the neutral axis will be making with the x axis. Now, please note that this angle alpha now not only depends on the sectional property ixx and iyy, but ixy, but it also depends on the applied moment. So, the orientation of the neutral axis will not only depend on the cross section, but also depend on the applied moment. So, if the applied moment changes, then the alpha angle changes. So, the orientation of the neutral axis changes as we change the applied moment. This is very much different from the unidirectional bending that you must have studied earlier, where the neutral axis position entirely depended on the cross section of the beam and not on the applied moment. Next, what we will be doing is to solve an example problem which will further give us clarity on how to use this equation to obtain the stress distribution in the cross section of a beam. So, let us do this example. So, this is the cross section of a beam. I will write down the dimension of this beam. So, this is 8, all the dimensions are in mm. So, this is 8, this is 80, this is 40 and this is 80. This thickness is also 8. Now, to this cross section, so this is the cross section of a beam, it is said that a moment of 1500 Newton meter is applied about the y axis. Applied about the x axis. Find the maximum stress developed in the cross section, in the beam or the beam cross section. Now, how do we solve this problem? The first step of to solve the, so we can write therefore that mx is equal to 1500 Newton meter, whereas my is equal to 0. So, there is no bending moment applied about y axis. So, if this is the case, let us draw the x and y axis. So, this is x axis, I am drawing them through the centroid. So, this is y axis and let this be the centroid. So, in order to find out the value of the normal stresses, the first thing that we need to do is to find out Ixx, Iyy and Ixy of the cross section. So, that is the first job that is needed in order to solve the problem. So, before we find out Ixx, Iyy and Ixy, since the cross section is highly unsymmetric, we need to find out the centroid of the cross section. Let C be the centroid and let us say that this, we are measuring this as x bar, the position of the centroid, and we are measuring this as the y bar, and we need to find out x bar and y bar. So, it's a very conventional way to find out the x bar and y bar. Let us first try to find out y bar. So, the total area of the cross section is 120 into 8 for the upper portion and 80 into 8 for the vertical portion, and that into y bar is going to be 120 into 8 into 4, that is this distance. So, this is the centroidal line and this is the individual portion. So, this is at a distance 4. So, we can say that this is 120 into 8 into 4 measured from the top portion, plus for the vertical portion we have 80 into 8 into, we have this as 40 plus 8, that is 48. So, if we do the calculation, then y bar is going to be 21.6 mm. So, this is going to be 21.6. Now, let us try to find out x bar. So, the same thing applies. So, 120 into 8 into x bar is going to be equal to 120 into 8 into, so the centroid is at 40, so this centroid is at 60. So, 60 minus, so we have to, so the centroid of another line of this is at a distance 60. So, we have 60 minus so 40 plus this distance. So, we have this as 120 into 24 minus 16. So, we have this as, we will have this as 24, and that is going to be equal to 120 into how much do we have? We have 36. We have 40, 20 plus 20 plus 4, sorry. So, this is going to be 24 plus we have 80 for the vertical portion into 4. So, if we calculate this, then x bar turns out to be 16 millimeter. So, x bar is going to be 16 millimeter from the outermost portion of the cross section. So, let us, if we, once we have found out x bar and y bar, then our next job is to find out the sectional properties, which is IXX, IYY and IXY. So, let us start with IXX. So, for IXX, let us start with the top portion. So, we will have 112 into 120 into 8 cube plus 120 into 8 into, we have this as 21.6 minus 4 whole square plus, for the vertical portion we have 112 80 whole cube into 8 plus 80 into 8 into, the distance from this is going to be 48 minus 21.6. So, 48 is the centroidal minus 21.6 whole square. So, this if we calculate is going to be 1.09 into 10 to the power 6 millimeter 4. Similarly, we can find out IYY, which is going to be for the top flange 112 into 120 cube into 8 plus 120 into 8 into the distance of that. So, which is going to be 24 into 60 minus 60. So 124 is the distance between this and this axis, and then we do it as minus 16. So that into that of whole square, plus we have 1/12 80 into 8 whole cube plus 80 into 8 into the distance, which is 16 minus 4 whole square. So if we calculate this, this is going to be 1.31 into 10 to the power 6 millimeter 4. Now let us find out the product moment of inertia, which is Ixy, which can be found out as, for the top portion, 120 into 8 into, we have to find out the distance from the axis, which is 8 and which is 17.6. So this centroid is, this distance is 8 and this distance is 21 minus 4, which is 17.6. Both are positive. Now for the vertical portion, we have 80 into 8 into, we will have it as minus 12, which is 48. So minus 12 is going to be 16 by minus 4, and into, we will have minus 17.6. So if we calculate this, this will be, sorry, this is going to be minus 26 point. So this is going to be minus 26.4. So if we calculate this, this will be equal to 0.34 into 10 to the power 6 millimeter 4. So therefore, we have found out all the sectional property Ixx, Iyy and Ixy. So let us now, what we have to do is just plug them into the equation and get sigma z is going to be, since my is 0, it is going to be mx into, if we plug in all the sectional parameters, so we can write this as mx, since my is equal to 0, Iyy into x minus Ixy into y by Ixx plus, we are going to have my into Ixx into x minus Ixy into y by, sorry, I made a mistake here. So this is going to be y. So this is going to be y and this is going to be x. Then I have Ixx, Iyy minus Ixy square. So now this is equal to 0, since my is equal to 0. So we are just left with mx Iyy into y. So we are just left with mx Iyy into y minus Ixy into x by Ixx Iyy minus Ixy square. So in this equation, let me call this as equation 1. So in this equation, we will substitute Ixy to be Ixx to be 1.09 into 10 to the power 6 millimeter 4, Iyy as 1.31 into 10 to the power 6, all in millimeter 4, and IXY is going to be 0.034 10 to the power 6 millimeter 4. So, if we substitute these values into this equation, then we will see that sigma z is going to be mx, if we and the value of mx is 1500 Newton meter. So, if we substitute this value, this will end up being 1.5 y minus 0.39 x. So, this is the expression that we are going to get. So, we can find out the normal stress at any point by substituting the value of x and y into this equation. So, let me call it as equation 2. So, if we go back to the previous case, we have obtained sigma z for this cross section to be 1.5 y minus 0.39 x. So, from equation 2. So, this is what we have found out. Now, how do we find out the maximum stress in the cross section? Now, we have to do inspection. We have to see the most likely the corner points are going to have the maximum stress because they have the maximum value of x and y. Now, if we investigate this, we will see that this point is going to have the maximum stress. So, for this point x is going to be equal to so let me erase this off. So, we have to do an inspection and see which point is going to have the maximum stress. So, one practical way to find out is to check at each point, at each of the corner point, this point, this point, this point and this point, to see if where the maximum stresses happen. Now, if we look into all these corner points, we will be able to find out that this point where x is equal to minus 8 and y is equal to minus 66.4 has the maximum stress, and if we calculate that, if we substitute these two values, that is x is equal to minus 8 and y is equal to minus 66.4, as in this equation, we will find that sigma z max is going to be minus 96 Newton per millimeter square. So, this is the answer that we are looking for. Okay. So, to summarize the process, if we need to find out the maximum normal stress in a cross section, we first need to find out the centroidal the sectional property about the centroidal axis, and once we find it out, we have to substitute in the expression for the normal stress sigma z, and we will get an expression in terms of the coordinates of a particular point, that is x and y. Then we have to substitute the coordinates of that point in that equation, and that will give the value of the normal stress at that point. Thank you.